This is Mr. Sorrentino again, bringing you this last video that we have to do for new material in this course. And that is section 6.7, Systems of Linear Inequalities and Linear Programming. So a lot of the information we're going to be seeing here is certainly a lot simpler than the things we had been covering in Chapter 6 prior to this. The only time we're going to have to use some information that we used in prior parts of this chapter is when we start looking at systems of inequalities and we have to know any specific points from them, which is what we do in linear programming. As far as though, graphing linear inequalities and solving systems of inequalities, you're not going to basically, just have like one set answer, even if you say, I'm going to solve a system of inequalities. What you're going to be looking for is a region on the graph that basically has ordered pairs that would satisfy the conditions of both, all three, four, all four, whatever, how many inequalities you got. But before we can start getting into doing multiple inequalities, let's see what we do for single inequalities and how we would go about graphing them. And I'm going to give myself some space on both sides here. When I have a linear inequality, which basically means I'm just going to have an inequality symbol where I normally have the equal sign, But as far as what I do to solve this, or what I do to graph it, I still like to put it in slope-intercept form for two reasons. One, it makes it easier to graph in the long run, and two, it lets me know where to shade along with that. So here's what I mean. Let's first put this into a slope-intercept form, which means we want to solve this inequality for y. So if I wanted to go through and do that, I would subtract 2x from both sides, and then I would divide both sides by 3. Making sure on that right-hand side I am distributing. And so I would end up with y is greater than or equal to negative 2/3 x plus 2. And so I would simply start graphing this the same way I would normally graph, any line. So I would start up 2 on the y-axis, and I'd find additional points by going down 2 and right 3. Of course, I could also go up 2 and left 3, just to get some more points. Especially if you don't have a ruler, which I'm going to make use of one here to make it look nice and neat. Now, before I start drawing a line with this, I do have greater than or equal to. So that's important because the equal to part means that things along this line satisfy the equation. So like, for instance, the point 0,2 is on this line. If I put 0,2 in, 0 for x and 2 for y, I would get 6. Is 6 greater than or equal to 6? Well, yes, it is. It meets the equal to part. So things along the line are included, which means I'm going to draw this as a normal solid line, as I normally would. And because I have this in the slope-intercept form, the fact I have a greater than means I should shade above the line. So ordered pair in that region would make this inequality true. More than likely producing things that are greater than 6. We do the same thing for b. I'm going to solve this one for y, so I'm going to subtract x from both sides. So I have negative 4y is greater than negative x plus 8. Now I'm going to divide by negative 4. When I divide by a negative in an inequality, I do have to switch around the inequality sign. There's actually a 1 here before, so I'm going to have negative 1 divided by negative 4, which is 1/4 x. And 8 divided by negative 4 is a minus 2. Again, I had to distribute that division. That's why it's important, just because I had a greater than or equal to sign or a greater than sign in the original inequality, if it's not in the slope-intercept form, it's hard for me to determine if I should be shading above or below without, putting some points in and seeing how it works. And it's certainly a way you could deal with it. I mean, this is certainly more of a shortcut. What I'm going to do is I'm going to graph this line again. So I'm going to go down negative 2 on the y-axis and go up 1, right 4, up 1, right 4, up 1, right 4. I can also do down 1 and left 4, as well. Now, when I do this, anything along the line 1/4 x minus 2 is not going to make this true. Like for instance, like the 0, -2, it's on the line. But if I put those points in 0 and 2, 0 and -2 for this, I would have 8 being greater than 8. That's not a true statement. So basically, anything along the line is going to make the left-hand side equal 8. Being equal to 8 is not what I'm looking for here. So that means that in this case here, this boundary line that I'm drawing is not included. So when I draw it, I do have to draw it dashed, which ends up it's the boundary, but it's not, anything on the boundary is not considered part of the answer. So when I draw this, I'm going to draw it dashed. So there's my dashed line. And then that it's in this form, I can now say, okay, well, I'm going to now let it shade below the line because it's less than. Another way of doing that, if you're unsure, if you did it right, is just pick a point that's clearly in one area or the other. I mean, if it's available, I choose the origin because zeros are easy to work with. And if I put 0, 0 in for the x and y, does it make it true? If the answer is yes, then whatever region the origin's in is going to be the solution area. If it doesn't work, it's not going to be. So the other region would be the solution. But generally, if you put it in slope-intercept form, the greater than or less than portion of your inequality will tell you above or below. So that's how you go about graphing linear inequalities. Now next, we're going to look at graphing systems of linear inequalities, which basically we're doing this procedure a couple times and we're looking for overlap. So let's have a look at that. So for part A of number 2, I have two inequalities. I have x is greater than or equal to -2, and I have y is greater than or equal to 3 minus 2x. The first one's not too hard to do because, I mean, if I had x equals -2, it's a vertical line. That means all my x's are -2s. So I'd be like doing the line that's right here. I'm gonna use the ruler again because sometimes when I try to do it without the ruler, it looks really wavy and stuff. I don't want that to happen. That's just an issue with the pen. So x equals -2 would be here. It's harder to do the above and below, but remember when I'm dealing with x's here, it's a solid line again because I have the equal to part. Being greater than -2 means I'm in this region over to the right. So I'm just going to shade that part here. In there. Now I'm going to look at the second one. The second one, I can rearrange it just a little bit. It's already solved for y. But it looks more like slope-intercept form if I have it in this format. So I know when I graph it, I'm going to start up 3 and go down 2, right 1, or up 2, left 1. And I would shade above that, but I'm only going to really shade what's already been shaded before. So the feasible region, or the answer to this, is going to be this region right here. I'm sorry if it seemed like it was doing a lot of jumping around there, but it was having some issues with the computer. So, but that region right there is where I would have solutions to this inequality. Let's try the next one. And right now you're not going to be able to do a lot of participating with this because of the fact that it's hard to put in graphs and inequalities and things like that. So, but let's look at the next one. And I want you to maybe pause this video a moment, try to see if you can make the system of inequalities for this, and then resume it to check your work with it. So to graph these, and again, this is an instance here where for some reason my the axes aren't showing up quite as well as I'd like to see them, so I'm going to put them in really quick. So, and I'm going to start with the two easy ones. I'm going to start with x is greater than or equal to 1. So here's where 1 is. It's a solid line because I do have the equal to part. And I would be shading to the right hand side. I'm not going to do a whole lot of shading because it's going to get really mixed as I go through it, but this right hand side is where I'm shading for that one here. So I took care of this one. For y is greater than or equal to 2, I'd have a horizontal line there, so I'm going to put that in. Again, it's going to be a solid line. And for that, I would be shading above. So we're looking at this region now here. Now I'm going to go to the top equation. I'm going to put that in terms of y, so I'm going to have 2y is less than or equal to negative x plus 10. Divide both sides by 2. I get y is less than or equal to negative 1/2 x plus 5. So it has a y-intercept of 5, and I'm going to move down 1 and right 2. So put some points in here, and I'm going to graph it now. Again, a solid line because it was the equal to parts in there. And you can see a lot of the linear programming problems, it's going to be the case. But for this region, since I do have the less than sign, and sorry if there's any jumping around going on here. There was some issues with the recording before. It's now going to be this region in here. I mean, because it's below the green line. And lastly, I'm going to, let's zoom out a little bit on this. Move this over. And now I'm going to figure out this one in terms of y. So y is going to be less than or equal to negative 2x plus 10. So I'm going to plot some points. And I'm going to graph the line. And now I would be shading below that line. So the overall feasible region now, I'm just going to graph this in a nice dark color, is this region right here. So in that little region in there, and I'll even zoom in on it a little bit, is going to make up every ordered pair that makes all 4 of these inequalities true at the same time. And this is a lot of what we're going to be doing when we're dealing with linear programming. In linear programming, we're going to get these inequalities from descriptions in the problem. We're going to find this feasible region. It might be the case we might have to eventually find like these intersection points. Now some of them will be kind of easier to find because we know the specific x value already and we know which equations it's going through. Other ones, like maybe this one right here, it might be a little harder to find because I had to find this, solve that system of equations to find out what that intersection point is, but that kind of goes back to the work we've done prior to this. So let's take a look at some linear programming problem and the process needed to do that. So the process of linear programming involves these steps here. You're going to read the problem because you're going to be given a word problem in all these cases, and you want to translate the information into a system of inequalities. These inequalities will be known as the constraints. The way you know these are going to be things that are, the constraints, because there's going to be another thing we're going to be looking for, which is an equation that will be known as the objective function. The objective function is typically, going to center around whatever you're trying to either maximize or minimize, and that's what most of these problems are going to be like. You're going to be maximizing or minimizing something, whether it's cost, profit, weight, whatever. Number of things, something that you don't know, you don't have any constraints on. The constraints are going to be limitations. You have to have so much of this. You have to have at least some of this. When you see those words involving specific things in the problem, those are going to define your constraints. So you're going to take the inequalities and graph the feasible region. And you're going to need to find the coordinates of the vertices of that feasible region. So that's where solving systems of equations might come into play. Because if you know the equation of the lines involved, and you don't know what either of the 2 points are, you might have to calculate them out. In other instances, you're going to know what the x value is. So you can probably figure out what the y value is pretty easily. And then lastly, you're going to use those vertex points in the objective function to see which one provides the minimum or maximum that you're looking for. So let's have a look at this example down here on minimizing cost, and we'll see how to go about doing this. I'm going to zoom out just a tad. So an animal feed is to be made from soybean meal and alfalfa. The mix must contain at least 120 pounds of protein, 24 pounds of fat, and 10 pounds of mineral ash. So it's these levels of protein, fat, and mineral ash that's going to be defining our constraints. Now, each one of these provides some of those, so that's where the rest of the inequality is going to come from. Each 100-pound sack of soybean meal costs $15 and contains 50 pounds of protein, 8 pounds of fat, and 5 pounds of mineral ash. Each 100-pound sack of alfalfa costs $8 and contains 10 pounds of protein, 6 pounds of fat, and 8 pounds of mineral ash. How many sacks of each should be used to minimize the cost? Now, a lot of people would look at this and say, well, I'm just going to buy the $8 sack of alfalfa. No, don't put any soybean meal in at all, just like, because it's $8 per sack. But you might have to buy more of that to get the levels you need. And you can say, well, I could buy less of the $15 one, less sacks, but I end up spending more nonetheless because they're more expensive. We want to see if there's a happy medium. So if I buy a combination of the two, would I be able to possibly minimize my costs as much? And that's what I'm looking to do, is minimize the cost. So when I start dissecting this problem, what I'm looking for is how many sacks of each. So that's going to be my variables. So I'm going to let X be the number of sacks. 100 pounds has nothing to do with anything here because the sacks themselves are 100 pounds. So, but I want the number of sacks of soybean meal. And I'll let Y equal the number of sacks of alfalfa. And that's very important. Our objective function I always find it's best to figure out what that is first. I want this objective function in terms of X and Y. It's going to be cost. We want to minimize the cost, so the cost is going to be, well, each X is $15, so $15 times X would tell me how much that would cost for the soybean meal. 8 times Y would tell me how much I'd be spending on the alfalfa, and adding them together would give me the total cost. So that's my objective function. That's what I will use later. What I want to have now are my constraints. What we come up with, our combination has to have certain levels of protein, fat, and mineral ash. I'll just do some abbreviation of that. Those are going to be defined constraints. Those are the ones that are defined outright, but there's also the fact that, I'm going to use the fact that I know that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. It's basically just saying that I can't have negative sacks of these items because that wouldn't make any sense with respect to this problem. And that's why, and that's already taken care of by the fact that we're only graphing in region 1, where I have positive X and Y's. So that's why it's set up this way. So these have already been kind of taken care of, but it's always important to kind of keep those in mind because some things are going to be implied. You should know that they have to be positive depending on the circumstance or what have you. So I need to come up with 3 formulas for this. So what I want you to do is see if you can come up with the formulas, the constraints, based off of protein, fat, and mineral ash for this problem. Well, since the soybean meal gives me 50 pounds of protein per sack, and the alfalfa gives me 20 pounds per sack, if I add those together, I should get the 120 pounds I need. That has to be greater than or equal to, because I need at least 120 pounds. If I have more, that's cool. That's why it says at least. For the fat, I get 24 pounds of fat for each 100-pound bag of the soybean meal, 8 pounds of fat from the alfalfa for each bag, and I need to get at least a grand total of, just want to make sure. Sorry, I had those mixed up a little bit. So I have to have at least 24 pounds of fat. 8 of that does come from the soybean meal. 6 pounds comes from the alfalfa. So I had those mixed up a little bit. And lastly, the mineral ash. I need to have at least 10 pounds of mineral ash. Each sack of the soybean meal will give me 5. Each sack of the alfalfa will give me 8. So these are my constraints that I'm going to graph and find a feasible region for. So what I'd like you to do is pause a moment and see if you can come up with your drawing of the feasible region and then compare it to mine when you come back to it. So with these constraints, I'm going to graph my feasible region. I'm going to do this in fast motion here and then kind of sum everything up when I get there. So there generally is my graphs and my feasible region. I made them a different color so I could keep track of them. I didn't show all the calculations I did to graph the lines, but when I put them in slope-intercept form, the red line goes, it has a y-intercept at 6, and it has a slope of -5/2. So I made sure I had that. The second one, the fat line, which I did in purple, has a y-intercept of 4 and has a slope of -4/3. And then the mineral ash one, a little bit more problematic because it has a lot of fractions involved. You put it in slope-intercept form, but it does have, it's easy to determine it has an x-intercept at 2 because 5 times 2 is 10 and plus the y would be 0. And then I just had to figure out what the slope is and use this, and the slope was basically a -5/8. So so that's what those lines are showing. Now, as you see here, the feasible region, because it's all greater than or equal to, and of course the axes are also included as well. So it has to be above. It has to be above the x-axis, to the right of the y-axis, and above each of these lines. If you see here, the mineral ash line doesn't really play much of a role in this. It's going to be the protein, the fat that really determine, how many of each to buy, because it just seems as though like the mineral ash will be satisfied if I get the protein and fat mixtures down enough at this point. So what I need to do now is determine the vertices for these. And some of them are really easy because some of them were part of the graphing process. So like this vertex here. Now it only has vertices at one end. It's not a feasible region that's been cut off, and you're going to see that a lot with situation where you have to minimize stuff. Is that you're going to see it's a pretty open feasible region and only has boundaries on like one side of it. So 0, 6 is one set. So basically that's saying, okay, that was one of our possibilities I mentioned before. Because it's the cheaper of them. That's buying all alfalfa, no soybean meal. This one down here is at 3, 0. And that would be the instance of me having all soybean meal and no alfalfa. But you notice it's only 3 sacks of that as compared to buying 6 sacks of that other stuff that's cheaper. There's also one other vertex here, and that's the intersection between these two, the protein and fat lines. And so what you need to do here is you would need to solve the system of equations 50x plus 20y is equal to 120, and 8x plus 6y is equal to 24. You have to solve that system to get that intercept. Now, so take a moment, go through any process you want, whether it's elimination, substitution, any matrix stuff, you're using row operations, Kramer's rule, whatever you want to use, and come up with a solution to this system of equations to find that third vertex. Just for the sake of argument, I'm not going to go through a process here because hopefully that you now have found out what the answers are using your own method. The answers should be essentially in fraction form 12 sevenths, 12 sevenths. If you didn't get that as a solution, go back and look over your method, try to find any errors you may have made along the way, and if you can't, try another method to see if you can get closer to the right answer so you know which method works best for you. So now I have my three vertices. There's no more vertices. These are the three I'm going to try out. So I'm going to now go back to my objective function right here, and I'm going to use that and come up with, okay, I have x's, y's, and cost. So I can either have none of those, 6 of those, 12 sevenths of those, and 12 sevenths of those, or 3 of those and none of those. And I put each one of these into that cost function. So 15 times 0 plus 8 times 6 is going to give me a cost of $48. That one's pretty easy to do, and so's the 3, 0 one. 15 times 3 is 45, plus 8 times 0, which is 0, it's going to be $45. So if I was just comparing, buying all of one versus the other, it'd be cheaper to buy all of the soybean meal because I only need 3 sacks of that and get all the nutrients needed, as compared to having to buy 6 sacks if I only buy alfalfa. Well, let's see if I buy a mixture of them, in this case basically 12 sevenths, which is 1 5/7 of a sack of each, will that give me a smaller cost? So if I do that, put 15 times 12 sevenths and 8 times 12 sevenths and add them together, I get approximately $39.43. So I'm just putting into this function right here. So that's the cheaper one to go with. Now it might be harder to buy them in realistic terms, but you might be able to say, okay, well say this is like a week's supply. You could buy 7 weeks at a time, which means you'd basically buy 12 sacks of each, and then you would mix it up and split it into weekly rations to give to whatever your animal feed. So, but generally, to minimize costs, 1 5/7 sacks of each feed would meet the conditions and minimize cost. And that is the end of this example, and that is the end of this video. So if you have any further questions on this process, please make sure to see me during office hours or ask about it during class time. And until I see you then, and since there will be no more videos, this is the last one. I'll see you around, and have a good day. And hopefully by this point you know where you are in the course, and hopefully you enjoyed this course overall throughout, or learned a lot from it, or both. So I'll see you around. Have a good day.